Good morning, everybody. Bright and early this morning. Cows are eating their breakfast, laying down, and I am prepping up the steam engine. There's my water source, and I'm prepping up, double checking everything and making sure, filling it up nice and slow here. Got some wood stacked for the fire. You can see we just filling it right up. I left an extra port there to quickly fill it up. So I got the garden hose in there just trickling away. Got our barrels here for our injection pumps. This is the Penberthy that is not working right now. We're gonna test another one. This is a Metropolitan that is working. I think we had a little leak on this one last time, but we're going to go over and see what's up with that one. But it does work. And we've got another bucket of water for that one. And we've got some paper and some dry wood in there to get going when the time comes. So it's still very early. Steam crew is not here yet. And I'll introduce you to those guys when they get here. But we are moments away from firing this guy up again. And it's super clean in there. Just a tiny little bit of ash from last time. We'll blow that out and brush it out. But we are moments away from firing this guy up. So hang in there, and I'll be back with you shortly.
Welcome back to the power plant. I'll start that again.
That's a hang on there. Hang on. We're here firing the boiler up. Braden, Phil, Max, Bobby, and another crew over there already talking. Got the fire going. Alex is going to tell us a little bit about the engine, the boiler, everything here.
So this thing here was built by A.B. Farquhar in York, Pennsylvania. Where it was built as a museum now. You can see other engines like this there. And it was built in 1927. And what it is it's just a locomotive type boiler with a single cylinder engine on top. They call it an overtype because it's on top. Undertypes had them underneath. Pretty self-explanatory. But this engine apparently drove a sawmill right here in the area, and then it was buried in a sand pit to hide it from the scrap drives of the war, and then it was dug up much later by someone else because I guess the original owners either forgot about it or forgot where it was or what have you. So after it was dug out, Brian here got it, and we helped him get it going. It came up in pretty good condition. I looked inside it, we hammered it out for thickness and all that stuff. And everything in there was a lot better than some of the things that are running around today at shows, ironically. So, yeah, that too. So we're gonna just go over how it works, and right now there's a fire in it and it's warming up. It's nowhere near steam temperature yet. And for this will be a video more or less for people who've never seen a steam engine before. So what you see on the outside, if you had an x-ray, right, that end there.
Let me zoom in there, let me get in there.
Yep, sorry about the crumpled up paper. Someone thought this was kindling. I left it in the firewood barrel, so that's my fault. Yeah, thanks, Phil.
Thanks, Phil.
Yeah.
All right, go for it, Alex.
So,
I'm zeroed in there.
Sure thing.
Don't move it around too much.
All right.
Go ahead.
So what you got in this locomotive type boiler, you got a furnace at one end called a firebox. You have a barrel with tubes that go through it, and then you have a part that is not part of the pressure vessel called a smoke box. All locomotive boilers are more or less this way with differently shaped fireboxes. Now, the firebox is not simply a furnace with walls, all right? The firebox consists of a box inside of a box. The inner firebox is a vessel that forms a combustion chamber, which fits inside of this outer wrapper portion, which is just directly connected to the boiler barrel. It's all one open space. Around this space, in this void, is water. This whole thing is a water leg. So the entire combustion chamber is surrounded by water, which means that the entire combustion chamber is an evaporative surface. The fire can transfer its heat energy to the water on every side. The fire gases have to escape once the combustion is complete. The only way out is through these tubes, which go through the barrel. They're also submerged in the water, all right? So these tubes are also helping to transfer the fire's heat energy into the water to make steam. And once they leave the end of the tubes, they get to the smoke box, where they are pulled up the stack by the stack's height and also by the exhaust steam of the engine. It's a nice system because the air comes in from the bottom through his fire grates, just like on a barbecue grill. The rate at which the fire can generate steam, the hotter the fire is, the harder the fire is drafted. The harder you work the steam engine, and you'll see this later, the more intense the exhaust steam blast is up the chimney, and the harder it pulls the fire gas through the tubes, so the hotter the fire becomes. So the harder you work the engine and the more steam you use, the more steam the boiler will make to make up for it. And if you run it properly, the pressure doesn't really change. Now, there's one thing about these boilers. Well, there's quite a lot of things about them, but as we're warming up, one good thing to talk about is you never want to warm them up or cool them down too quickly. Metal expands and contracts, everything expands and contracts when it gets hotter and colder. Metal, if you do it too quickly, can develop lots and lots of cracks, especially on an old boiler like this. So you can tell that a boiler's in good condition a lot of the time because it will have been treated nicely, it'll have been warmed up slowly, cooled down slowly at the end of the day. Once you're up to operating temperature and pressure, you can work it as hard as you like because the pressure and temperature in the boiler, if you're a good engineer, stays about the same. And no matter how hard you fire it, the boiler pressure always corresponds to the temperature and vice versa. We don't talk about superheat because this engine doesn't have a superheater, but every time you have a steam boiler, the pressure of steam, saturated steam, we call it saturated because it is saturated with energy, not because it is wet. Wet steam is not saturated steam. It's actually got less energy than saturated steam. But every pressure of saturated steam has a corresponding temperature. 100 psi steam will be something like 320 degrees Fahrenheit. I don't have the steam tables in front of me, but every single time you have a pressure of saturated steam, it has a corresponding temperature. So if you keep this boiler right under the safety valve at 119 psi or something, no matter how hard you fire it, as long as you have water on all the sides of the firebox, which is very important, it will never exceed, the metal will never exceed a little bit beyond that saturated steam and water temperature in the boiler. So if we're running at 120, which is what our safety is currently set to, it'll be something like 330, 340 degrees. Like I say, I don't have a steam table in front of me, but the metal will be a little hotter on the side with the fire, but generally the metal will not exceed that temperature, and that's quite low for boiler steel. We're not going to rush it. It'll take probably a couple hours to get steam up. We'll rejoin you then.
You have an adjustable.
What are you working on, Phil?
I want to tighten these packing nuts are like all the way back.
All right, let me grab one.
Oh, are they
hang in there.
The hair creates.
All right, here we are again with Alex. He's going to explain a little bit more stuff.
So we got a fire going in there. Not a big fire.
Let me get in there.
Yep, don't melt your lens.
There we go.
But you want to
Okay.
warm up. You want to warm up slow because, like I said, if you do things too fast with the boiler, if you warm them up, cool them down too fast, if you introduce too much cold feed water all at once, it really hates you. For reasons we'll get into a little later. But, yeah, right. But one thing we got to do.
Yep, there's
we
Phil
gotta
again.
make sure we
talking about his ex. Okay, gotcha.
We got to make sure we vent oxygen from this boiler as it's steaming up because the water will have dissolved oxygen in it and there's air on top. So at the very least, you leave the top tricock open. If there's any other valves you can on this engine, like the blower or what have you, you leave them open so you can drive off as the water begins to boil. You drive off all the oxygen in the water and above it. And you do that for a considerable amount of time. Like even when you're getting up to 10, 15 psi and there's steam coming out, you want to leave those open for a while because with that steam coming out will also come out oxygen and air. And it's very important to get that out of the boiler. We got the water's on the boil now. Got a little bit of steam, mostly air, venting out of the top tricock. That's our main air vent. One thing about valves, especially globe valves, but all valves really, never open them wide. Always go back a quarter turn, because if you open them wide, first of all, they jam, and second of all, If they're like that and the temperature changes, like if they go from cold to hot or especially hot to cold, they thermal bind and you will never move that valve without breaking it. So always go back a quarter turn with any of these. One thing we got to do now that we're almost ready, we had these isolated. We're going to open them up. These things here are the isolating stop valves, right, that come from the injectors. When a boiler runs, and you use steam for various processes, heating things, driving engines, turbines, whatever. Of course, the water will boil off and the water level in the boiler drops. The number one rule of steam engines is never let the water in the boiler go too high or too low. If it goes too high, you'll feed water into your engines and other processes and destroy them. And if it goes too low, the metal that should be transferring heat to the water will instead just melt itself and you'll have a big explosion. And that's what happened at Medina, Ohio, and Gettysburg, and a couple of these other places where these idiots had no idea what they were doing. So you have to put water in the boiler as you're running it to make up that, to keep that level stable. This is an injector. We'll show you how that works a little later when we have steam, but this is a device that forces water into the boiler using steam pressure, or steam velocity actually, and it travels. This is the pipe it gets from the injector into the boiler. You've got a check valve, which is a valve that only allows things to flow one way and not the other way if it's working correctly. This is a flap disc type. You can tell it's facing the right direction if you're a moron because there's an arrow, but if you know these valves, the disc hinges on a pin which is in here, and you always put the pin on the side that is coming from the delivery so the disc will hinge in this direction. This is a stop valve which is present in case this check valve does not close. And one fairly common problem, especially with these cruddy modern check valves, old fittings are always better if in proper condition, is if you run the injector and get the water going in the boiler, when the time comes to shut off the injector, sometimes this valve will not seat properly. You'll get water flow out of the boiler back through this pipe and out the injector overflow, and you'll think, oh, the injector's still running or the steam valve is open, but it isn't, and it'll be this. And what you can do is gently tap it, and if that doesn't close it, you can close this valve if you absolutely can't get it to shut. So this is like the emergency shut off. It can always shut it. And there's another thing about valves, right? These globe valves are directional. The stem, you see, rises when you open it. You always want the delivery to be from underneath the valve seat. If the valve stem breaks, you can close it and open it, and the valve will still operate in emergency. If you have it on the other way, the pressure will seat the valve closed, and that's beneficial in some cases, but in these cases, you always want the delivery under the valve seat. The other thing is, when you have a valve on a steam line like a throttle, you'll never be able to open it with the pressure over the valve trying to seat it if it's a gigantic valve, and it can be stressful on these small guys. You'll get them open, but you can break things. We've got provisions for extra things like steam feed water pumps or additional injectors. There's another injector on the other side. We'll talk more about checks and non-returns and stuff, whatever you want later. Now that we're on the side of the boiler, you see I've drawn, so this drawing oriented that way would be a section right across this firebox. And these stays, right? Remember how I said that this space, here's the water level and here's the sight glass taken off. This whole space is full of water and steam. This whole firebox is transferring heat from the fire through its walls, through the side walls and the crown sheet to the water. This whole space, because this whole space is the boiler, is pressurized, so it's trying to push these walls apart that way, trying to push the inner walls inward and the outer walls outward. So just like a structure, like a bridge, you have these stay bolts that cross between the walls loaded in tension. You can see their ends here. And the way they're put in is the stay, you tap the hole from the outside into the inside, and the stay bolt is this big long threaded piece. Sometimes the middle isn't threaded. And it has a square or a hex on the end, and you turn it in with a wrench, and once it's in, you rivet the ends over on the outside and inside to make the steam seal, and you grind off the hex or square that you've used to drive it in, and that's why they look like this.
Alex, tell us about the telltales.
Yeah, telltale holes here. If you have a stay bolt break in the middle, these telltale holes go partially through inside, and what will happen is if you have a stay bolt break, the water will find its way from the crack into the telltale hole, and you'll get a jet of steam or water out the stay, and you'll be able to tell, oh, that stay's broken, it needs to be replaced. Crown stays don't have it. These are the stays that come down from the top that support the crown, but they're all loaded in tension, and they just hold the boiler in shape against that pressure. Rivets are interesting. I love riveted boilers. First of all, they've got a lot of give to them, so they expand and contract better than a welded boiler does. Second thing with rivets is you don't have to worry about the thermal stress and heat treating with welds. All right, and you'll see this sort of line around the rivet. That's a caulking line, impact caulking. The way you install these is you put the sheets together, you drill your holes, you drive the rivet in red hot, and you drive it tight. And when that rivet cools, it pulls everything together into a tight form. That's why we drive them in hot. And then to make the actual steam seal at every seam, and sometimes around the rivets if they leak, you have an impact gun with a tool on the end. It's called a caulking iron. And that impact will make a steam seal by mushing the metal sheets into each other. So it's not anything like caulking on windows or houses. That's just not how it works. In fact, I've met people who think that's what it is, and that's just a big problem. But caulking is when you impact seal seams and sometimes rivets on one of these boilers to make a steam pipe joint. There's another thing that's interesting about this boiler. It's fairly unique. There's two doors, right? Now we had this moron named Jake Templin, who's one of these self-declared experts, who tried explaining to people that this was a wet bottom boiler, which is where the instead of a solid mud ring with a grate on the bottom, there are these boilers where this water wall goes all the way around and the air enters from the bottom and the grate's kind of halfway up in the water wall. I should draw one for you later so you can see how they're built, but he thought that this was the damper, and it isn't. You have one door for a thick wood fire bed, and you have another door for a very thin bed if you're running with coal or if you're running with a very light wood fire. So this is a bottom fire door, and the grates are underneath that. And that's a feature you don't usually see. Usually it's just one fire door. In a few minutes, when we get a little more steam pressure, we be sure that the air is almost entirely vented out. We'll close the top tricock, and that'll be that. Oh, and there's another thing to mention too. So you'll see the water level. We started at about 1/3. There's this thing in a boiler called shrink and swell. Very important. In fact, if we have a seltzer bottle anywhere around here, I do in the car, I'll show it to you. But we have bubbles of steam in here. If you suddenly demand steam from the engine, or from anything, like an open valve, the bubbles will expand and raise the water level in the glass. And if you make a demand of steam that's too quick, like you open up the throttle on a big engine down on a steam line in a factory, you'll see this glass down here shoot way up. You have to be careful. And another thing is if you're running engines down the line really hard and there's lots of steam coming out of the boiler and your glass is reading a good level and then someone shuts off an engine or a turbine, you see the glass fall because those bubbles will stop expanding and flying to the surface, and you'll have to get that water level up. So it's always good to plan with your firemen and open things up slowly and close them slowly. And I'll demonstrate that with a seltzer bottle in the next.
Why don't we demonstrate it with the engine itself?
Yeah, we can do that
later
too. But a seltzer bottle has clear walls. It'll show you a good idea of what's going on inside.
That's true.
All right, we good?
Yeah, I'd say we're.
You have to interrupt the video then.
Thanks, Max.
God damn.
Start diving.
Go for it, Alex.
All right, so this little thing here is a steam blower. All right, this boiler doesn't have a steam dome or a steam turret. It just comes off the top of the barrel for everything. But this valve, all it does is it lets steam flow up a jet, just a pipe in the chimney to pull the combustion gases through the fire when the engine isn't running. But because we have such a tall chimney, we don't really need the blower. Just figured I'd show you that it's there.
Perfect. Go ahead, Alex.
So, cleanliness is extremely important for a boiler. Before we fired this up, we spent like 3 days in a row just washing everything out of it. The way you wash out and otherwise get access to one of these boilers, these oval or elliptical shaped things are called handholds, and this cover is seated by the steam pressure against there, but you can take that cover completely out and you can get your whole arm in there and cleaning tools and what have you and spray water and wash out the boiler, and they're everywhere. They're on 4 corners. There's one on the back head on top. There's another in the bottom of the forward flue sheet. Some boilers have them in even more places than that. But on one of these boilers, when it's running, just like when you have a cooking pan or a kettle, when you boil water, the steam that leaves is just pure water, so all the dissolved solids in the water are left behind, right? And they're left in the kettle. That's where you get that free white scale or whatever you're left with, whatever nasty things the treatment company's putting in the water. But in a boiler, they accumulate in the lowest parts, such as the bottom of the barrel and the bottom of this water leg. In fact, the piece of metal on the bottom that holds the sheets together is called the mud ring, because that's where all the impurities tend to collect. There's a blowdown line, which you can vent those impurities. If you properly treat your water, they stay loose, and if you vent them under pressure, they all fly out. So we've done a sort of a power plant scheme here. We got two valves, one in front of the other. One's the quick opening and the other's the slow opening, even though they're both slow opening valves. But I'll just blow down right now at about 25 psi so you can see what a blowdown looks like, and also to clear out anything that's accumulated in there.
Go for it, Alex.
Yep. Just make it a short one.
Yep.
So that's good, nothing too concerning out of there. And another thing about blowdowns is you never want to open them or close them quickly, because you can put tremendous stresses and forces on the boiler sheets. And we use these valves because it takes a while to get them open and shut, which kind of forces you to do just that.
Hang on. All right, here we are, guys, creeping up on 50 pounds. Pretty soon, we'll roll it right over. Alex, tell the people why this is an overtype and we don't run it backwards under.
So it's an overtype. You rolling?
Yeah, go ahead.
It's an overtype engine because the engine
why.
sits on top of the boiler. That's pretty straightforward.
Yep.
There's one important thing about stationary horizontal engines. You want them to run over. That is, the top of the wheel is going away from the cylinder, and the reason for that is the load on the crosshead when the main rod is up and traveling away is down, and when the main rod is traveling toward the cylinder, being pulled toward it, the load on the crosshead is also down. If the top slide bars of the crosshead or whatever is guiding the crosshead on any engine fails, if they fail, instead of flying up in the air and through the roof, which on this thing would be anywhere from mildly disastrous to inconvenient to a giant mill engine where it would definitely be disastrous, if the top guides or anything like that breaks, going over, the loads on the crosshead being down will stop pieces from flying up in the air, which is very bad. So on this thing, this direction is proper. And there's all kinds of museums that have these engines, or even worse, big coreless engines where they're running the wrong direction and it's just not right. And if you have to, if you're driving something that requires it to go a different direction, you can transmit it by crossing a belt or running it through a gearbox with two pinions or anything like that. But the engine should always be going over.
Okay, good tips, Alex. Good tips. He's the only guy with steam credentials. He's working at a steam plant. Look at him. Take a bow. Come on, man. Come on. Fantastic. Okay, go for it.
Not yet.
Go for it.
Hello. So, we're about to run the engine here. What I want to do is I want to crack the valve and warm it up. You'll see the that's the exhaust. That's condensate coming out of the exhaust. What's going to happen is I'm going to introduce steam to a cold cylinder, and the steam's immediately going to condense. And what you're going to hear is a lot of gurgling and spluttering. That's just the condensate coming out of the drains. And the exhaust.
Yeah, we can hear
What
it.
we want to do is we want to run the engine when the cylinder bore and the valve chest are hot. Because if we get a slug of condensate in there and while we're running the engine, water condensate's not going to compress, and we could blow out a gasket or blow the head off or something, which is no bueno. So we're going to take it nice and slow.
I'd warm the chest up first.
So, oh wait, do we have our governor?
Yeah, I wouldn't fuss with that. It is what it is.
The governor is cracked. Yeah, you'll be all
The
right.
governor is cracked?
Yeah.
Okay, we need the governor cracked because the governor is like, it's an automatic throttle in a sense on this engine.
With an emergency stop.
So if you come over here, notice I have the engine where it is for a reason. I have it,
Okay, I can see it.
I have the crosshead about here. This is the end of the crosshead, which is the end of the, which is basically the end of the piston.
Yep.
Over here. I have it over here because when I introduce steam in order to turn over the engine, it wouldn't turn over if it was either at dead center, just either end of the piston. There's just no room for the steam to come in and expand and push the piston. So you want it a little off dead center when you're starting.
Gotcha.
You want to open my little lubricator.
Yeah, just keep warming the chest right now. Just put it off some water.
Why don't I try? No, we're not there.
Oh no, not yet. Wait.
What do you got going on this side, Alex?
All right, so this side here, right?
Hang in there.
All right. First of all, disclaimer: I didn't put these valves on. They're just barely acceptable. We got to get proper valves on there, but they do for now. We got a steam chest. All right. In here is a valve. Kind of looks like a table. It slides back and forth over ports. It's a flat valve called a slide valve or a D valve. If you look at the side, it looks like this. I should have drawn it. There are 3 ports in there. Left, right, and exhaust in the middle. When the valve is in one position, steam can flow from this chest, which gets pressurized with steam from the boiler and the throttle. Goes down that port, pushes the piston this way, at the same time exhausting steam from the other port through the D cavity to the exhaust port and up the chimney. The valve moves over, it does the same thing backwards. It admits steam to the other side of the cylinder and exhausts it from there. And in certain positions in between where the valve overlaps all the ports, no steam is flowing anywhere, and you can get expansion of the steam by cutoff, which is where you stop admitting steam to the cylinder and the remaining steam inside it at high pressure expands and yields mechanical work to the mechanism by getting bigger instead of just allowing more steam in. And if the exhaust portion closes, when the piston is coming toward it, you get something called recompression, which is where a steam cushion bounces the piston back. It means you have to admit less on the next admission stroke. A single valve engine like this is nowhere near as good as doing that as something like a coreless engine, but it can do it if properly designed. When the cylinder is cold, right, we're warming it up, feeling it all the time as we go. When it's cold, you get water in there because the steam hits the cold walls, especially non-superheated steam, and it turns into condensate water, all right? And you have to get it out because steam is a gas, like air or really any gas. You can compress it and squeeze it. You cannot compress or squeeze water, right? So if you have water in the cylinder and the piston comes up against a water slug, that water is not going to move. You could blow the piston head off, or you could blow the other end off. You could do many destructive things. Blow the rings into pieces, break the piston, damage the engine. So it's very important to get it out. We have one drain for the valve chest, one drain for one end of the cylinder, and one drain for the other end of the cylinder. Right now everything's open, Phil's evacuating it, but right now we've got mostly steam and very little condensate coming out. We've had it going like this for a few minutes, so Mr. Phil, we're going to choke back the chest drain so he can get a plenum of steam in there to start it. And I would say he's in a good position on the crank. Since we're running over, it's right after the start. That port is going to be open on this side, this port. It's going to force the piston that way.
You get steam out of the chest drain and condensate?
Yeah.
All right.
Okay, we're back on Phil's side. What do you got going on now, Phil?
All right, I'm going to try and turn it over. You ready?
Get the pump started.
All right.
Okay, here we go. There she goes. We are living now.
Ta-da!
There it is.
That's it. We're just going to throttle it nice and easy.
Nice and easy.
Nice and warmed up. And we're going to close those cylinder drains when it's just steam coming out and not condensate.
Okay, coming over to take a look. What do you got, Alex?
closing them off very slowly, not completely closed.
Okay.
Especially since this is a saturated engine. There's
Yep.
no superheat. So,
Yep.
see, we got a little bit of water coming
Just
out.
kind of just keep them cracked.
Yep. And what we'll do eventually, we'll shut the chest drain completely because we need that to ensure that the oil from the lubricator stays inside.
Okay.
We'll probably leave the cylinder drains just weeping very gently.
Okay, we got the governor spinning for the first time.
Yep.
Brian,